Hello all and welcome back. So in this video, let us continue our discussion on queues and now let's see how we can implement our queues using a linked list. So let's get started. Now in the last videos, we saw that how using a list, we were able to implement our queue. Now to implement the same using the linked list, we again will have to make sure that each and every operations which we have discussed for our queues, we are able to do efficiently using a linked list. So let's see the operations. First, let me draw a queue. A queue we can actually draw like this. Great. So again, this is the out and this is our in. If this is the in, this will become the rear end and this will become the front end. Great. So cool everyone. We have the queue in place. Now let's think and discuss about linked list a little. We know that in linked list, we have a node, right? That's the most basic fundamental unit of our linked list. If we have to store the data, right? Let's say if I'm entering 1 here, then of course that will transform to a node which is getting created in my linked list, right? So if I've added 1 here, then for sure there will be a node which will be created in my linked list, right? In which the data is going to be 1. Cool. So yes, as of now, of course, we have just added one element. So let us just first think and then we will see each and every operation. Okay. Let me move this. Yeah. Great. So now moving forward, if I have to, let's say, add another element, let's say 2, how should we do that? Okay. In a linked list, I am aware that again, a node will sure be created. For sure, this node will be created. And I will have to see how I have to add this, right? So in the stack implementation, we saw that how the basic way we handle a linked list, that is by adding towards the tail, was not optimized enough. But is it optimized enough for a queue? Let us check the same. Let's say I am adding 2 here and then I am, let's say, adding again another 3 here. Okay, so this can be a node for 3. Now what I'm saying is that this is 3, 1, 2 and 3. Great. What I'm saying is that I have a head with me. I have a head with me, which is this. Now if I want to add anything to my queue, that will transform to adding element in a linked list like this, where they are connected with each other in a sequence, just like we have 1, 2, 3 on our screen. Now, let's say I want to add another element which is 4. That is going to create a node towards the end, right? Great. So if I have to create a node, then of course, one way is that I create a temporary, which is equals to head, and I make it go to each and every node and then get added towards the end. Something which we did in our take input function initially, if you remember, we were creating a temporary variable. Then I was trying to reach to my tail, which in this case is this. This is my tail. And then we used to add that. Okay. In queue, I believe that's a little bit unoptimized approach if we are adding it like this, because that would mean that, let's say, your queue is like this. Okay. Your queue is like this. This is the overall uh, counter where you are making a queue. Okay. Let me draw this. Yeah. So this is the overall counter where you are making the queue. If any new person is coming, you are effectively asking that person that, hey, go through each and every of these person and then get added into it in the end. Okay. Because this was my first index, first element. This is the second element. This is the third element. You are asking me to go through each one of them. Okay. It is the same as if, let's say, it's a 1 kilometer long queue. You are going to the starting and then just traversing 1 kilometer to get added in the end. Again, I believe a very good case will be if we maintain a tail here, just like we did in take input function, so that we can add efficiently. So instead of me traversing the whole queue, whole linked list for a new element, I will just say that, hey, this is from where you can enter. This is the tail. Okay. And this is the head. You don't have to go to head and then traverse the whole queue. No, you just get added yourself in the tail. which I believe is a lot efficient, which we can normally do, right? Because in current form, it will be just having something like this. We can add it here, right? And once I have added it here, then my tail will change. So tail is going to become this fourth. Just like normally we did the add input, but I'm telling you what is the problem if we don't maintain a tail. It will again be an ON approach, which we want to avoid. This is going to become my tail, and I'm fine with it. Okay. So on that note, seems like the NQ, we will be able to do NQ. Okay, everyone. So we will be able to do the NQ operation. Let me just wait 1 second. Yeah. For the NQ operation, we are able to work it out. NQ possible in O of 1. Okay. But one thing to very important remember, we will have to maintain a tail. Just when we maintain a tail, that is where we can do it in O of 1 time. Okay. Great. So let us now do the next operation, everyone. Let us see which next operation we can do. Next operation now can be front. Okay. Now we know that in front, we just have to tell that what element is the one to go out, which is in my front of my queue, this front. I believe it is very easy. It is just an O1 operation again. Whatever is there in my head, I can just return it. So this becomes head dot next. Again, if the head is not null, this is the overall operation which we can do to get the front, the element in front. Okay. So I hope till now these two operations are clear. We were enqueuing, and as of now we are just maintaining our queue in a similar way. In a similar way, the way we normally maintain a queue. So we are not adding from head. We are just checking if normal way of maintaining the linked list is helpful or not. Seems like as of now I'm able to enqueue in O of 1 and front also in O of 1. Now let's see the next operation, everyone. Third operation can be DQ. So you have to remove and give me this particular element. I believe DQ also is very easy. What you can do in DQ is you can just say head.next is the data. So we can get the data using front. And you can say that your head become the next one. So for this example, let's say if I have to remove this one, okay? So I will have to remove this one from here as well. What I can do rather than removing, like of course it will be removed if I just do this thing. I will ask my head to go and point here. And now if you will see, I have this particular linked list as my queue where 2, 3 and 4 is there. In a similar way, I have 2, 3 and 4 only. And seems that though in stack this was giving an error because we have to remove the last element which could have been 4 in stack. But in queue, it's working absolutely fine because the element which came in first, the FIFO principle again is valid. So because of my FIFO principle, I am able to do the same DQ operation in O of 1 as well. So again, it's in O of 1, right? Great. So I think as of now, we are able to do these all operations in good time complexity. Now let us see the next operation, everyone. Next can be size. Now talking about size, I think this is something which we will have to see because yes, we have the head. Yes, we have the tail. So we have the head with us. We have the tail with us. But this doesn't give me the information that how many elements are in between them, right? So I have the head, I have the tail, but between them, how many operations are present? How many nodes are present? That I don't have an idea. So either I will have to start from my head with a temporary variable, let's say temporary, and keep on increasing the way we used to find out the length, keep on increasing my temp until I found the tail. So that is one way of doing your overall execution of this size operation. That's one way. Second way, which I think we saw in stack as well, is we can maintain a size variable or length variable. And anytime you are adding anything to my length, I'm going to just increase this. Anytime you are dequeuing anything, I'm going to decrease it. Okay. So I hope this is clear, everyone. to do this operation in O of 1, okay, it will be better if we maintain a length variable. Will have to maintain a length variable, right everyone? So we will have to maintain a length variable. 1 second, yeah, for O1 approach. I hope this is pretty straightforward for O1 approach, right? Else, of course, it's going to take a lot of time, which can be problem. Great. So cool everyone. Now let's see the last operation which we used to do, which was is empty. I think this is a lot easy now because we have the size. We can just check if length is 0, or else we can check if as our head is none, right? If our head or tail is none, this can be very nicely done. So length 0 or head none. Great. I think if we do all these operations pretty nicely, then yeah, we are at a good place to actually implement each and everything in O of 1 space. So in this particular use case of Q using linked list, and I'm pretty sure that these notes will be a lot helpful to you to understand and remember, we don't have to change the way we maintain our linked list. We are able to do each and every operation in a good O1 time complexity just by maintaining the linked list with head, tail, and size. So if we are able to write normally the code which we used to do for linked list, we should be having a good accuracy for each and every of these particular operations, which I have to perform on my queue. Okay. So great, everyone. I hope all these operations were clear and the overall mindset on how we think about these operations is also clear with respect to a data structure in backend. Because see, the reason I'm doing this is to make sure that tomorrow, if you get some new data structure which you have to implement, okay, let's say a DQ, any circular queue, or any other thing in general, something which you want to learn about in future video as well, you are well equipped to think and implement. I don't want any of you to remember that head, tail, and length we take. No, that is not something which I want all of you to remember. I want all of you to understand that from where this understanding comes. That hey, these seems to be the variable. Why I want you all to understand that why we are taking this length variable, why we cannot function without it. Because if we don't take it, then ON approach will be there to find the size. Okay. So please make sure that you understand this whole process. And if you're able to, then implementation will not be that difficult. But if you try to again remember that, hey, in linked list, I used to take these three variables, then it's going to be a problem. Okay, everyone. So I hope it is now a lot clear. Please make sure that you actually understand the process and try to implement this once at your end. And we are going to meet in the next video where we will try to implement the same from scratch.